What if I told you that half of the universe has gone missing? Shortly after it was created, half of the universe disappeared. Okay, so we're going deep here. We're going to talk about mysteries of the universe today. And I'm going to have to answer some questions for you. So, what happens if time runs backwards? Why is the universe made of matter instead of antimatter? Good question. Is right better than left? Do you know? Is right better than left? No? Is there an anti-universe? Thought about that one? Can you blow up the Vatican with antimatter? Does antimatter fall up when you drop it? Something totally different sometimes. We don't know. Sometimes we don't know. You could if you had enough. You never will. We don't know. Thank you for listening. Protons, neutrons, electrons, the only three particles that make all this stuff up that we deal with every day. Add some light, and you pretty much have your daily experience. There's another possibility, turns out. Take quantum physics, that's the physics of really small things like atoms. Niels Bohr, famous Danish physicist. I'm a professor in Denmark, I must talk about him. You add small physics to fast physics, that's Einstein, right? Relativity, things moving really fast. You try to unify those two theories, and you get antimatter. A guy called Paul Dirac, back in the 1920s, invented the idea of antimatter. Let's see how he did that, because it's one of the biggest intellectual leaps in the history of physics or science of any kind. And I'm going to illustrate this with a simple problem. We'll call it Farmer Jensen's paradox. So you want to make a field that's 10,000 square meters, but it's square. And you ask, how long is each side of my field? Okay, so you know some math. You put in an equation, s squared equals 10,000. You can solve that. The answer is 100, right? 100 meters. 100 meters by 100 meters, 10,000 square meters. But wait a minute, minus 100 meters would also work, right? Minus 100 meters times minus 100 meters is also 10,000 square meters. But don't be stupid, that's not physical. A negative length has no meaning. This is exactly the problem that Dirac faced when he made his theory. He got things that had negative energy. 99.999% of the world would have thrown that out. Said, in the bin with that. That can't be right. That's not physical. Not Dirac. He said, I'm right. And the dude doubled the universe. Okay, what he found, these solutions were antimatter. Let's talk about antimatter. For every one of these particles that we talk about, the protons and neutrons that make us up, there's an equivalent antimatter particle. Okay? They can't coexist, these two things, right? They have opposite properties. They're like a mirror image. So if a proton has a positive charge, an antiproton has a negative charge, and so on. Think they have the same mass. These are experimental questions, but that's what we think. These two things can't coexist. If matter and antimatter meet, they annihilate. And that's where the science fiction comes in. That's the really cool part. This is the most violent thing we know about. Putting matter and antimatter together, that's the highest energy density. So for a hydrogen atom, I could also have an antihydrogen atom. Right? Those two should be the same. But for some reason, there's no antimatter left. Our theories tell us that these things must behave in the same way. That means I could build a universe out of antimatter. Okay? We have no idea why the universe chose matter. This is the anti-periodic table. The only thing that's ever been made in my experiment or any other experiment is antihydrogen, number one. in the anti-periodic table. We've seen some helium, that's number 2 atom, a couple of times in collisions, but we can't work with it. Okay, what about the name, antimatter? It's kind of aggressive. We do something at CERN, where I work in Geneva, put it up, publish it, and these crazy people on the internet make a great video. Say, CERN opens gate to hell with antimatter. You know, the antimatter, antichrist, it must all be the same, right? So how about alternative matter? It's a better name. It's less aggressive, right? But there's a serious point here. It is an alternative to normal matter. How do I know any of this stuff? What's the most famous equation in physics? E equals mc squared, right? So what we do, we get some energy E, that's what the E is, and we use it to make some mass M, right? That's what this says. Energy and mass are equivalent. C is the speed of light. It's just a number, okay? So we, especially where I work at CERN in Geneva, we're good at taking E and making M. That's what these big colliders, these big accelerators do, okay? So you can run some particles into some stuff, some collisions happen, some magic happens, some other stuff comes out the end, and maybe it's something new that we've never seen before. That's the whole idea with these machines. Or you can run particles into each other. Boom, something new will come out sometimes. That's why we're always going to higher and higher energy to try to see something we've never seen before. Okay, now here, if you don't remember anything else today, remember this. If I use E to make M, I have to make equal amounts of matter and antimatter. That's a law, as far as we know. It's an observational law. The second thing you should remember, if you don't remember anything else, is that you never know anything until you've observed it. That's the fundamental precept of the scientific method. You must observe it. You must reproduce it. All right? So as far as we know, this is a law. If I want to make a proton, I have to make an antiproton. If I want to make a hydrogen atom, I have to make an antihydrogen atom. That's a fundamental law. But now there's a problem. Because we know about this thing called the Big Bang, right? That's the beginning of the universe. A whole bunch of energy shows up. Boom! The universe starts expanding. Things get created. But wait a minute. I just told you if I used E to make M, I had to make equal amounts of matter and antimatter. So where's the antimatter? As far as we know, the universe around us, you and I, we're made of normal matter. And the answer is, we don't know. We have no idea what happened to the antimatter that should have been around at the beginning of the universe. I like to call this question 0. Why is the universe still here? Right? We simply don't know why these two things didn't just annihilate. So there might be some asymmetry, some slight difference between matter and antimatter that we haven't identified yet, but we'd like to look at. Let's talk about asymmetry. One interesting symmetry about the laws of physics is that the laws of physics should work equally if time goes forward or backward. So here's my daughter on the swing. You see, one way to check this stuff is to make a video and run it backwards. If you can tell the difference, then that's violating this symmetry, time reversal we call it, okay? Is that a symmetric situation? Yeah, right? It's an oscillator, she's going back and forth. I could have lied with the arrows. Here's another situation. Is that a symmetric situation? No? You're all wrong. Turns out that's the same situation. If I launched my daughter up the slide, it would get exactly that. It's harder to do. A better way to think of this, maybe I have a slide and then another one, and if there's no friction, she would just go up and down, right? So it's the same thing. What happens if I change all the matter in the universe to antimatter? Then I'm going to switch all the dimensions. Right's going to be left, front's going to be back, and top's going to be down. Okay? I can do that. And now I'm going to let time run backwards. Okay, this is a very abstract thought experiment, but what happens? Turns out I should get the same universe if I do that. We call this CPT symmetry, right? Most theorists are absolutely convinced that this is fundamental in the universe. If I actually could do this, I would get the same things. These guys have never been right before. Each one of these symmetries was at one time thought to be exact. We now know that none of them are. Maybe the combination is. So what do? The theorists can't tell you what to do about the antimatter, so we go looking. We can look at a big experiment in the LHC. There's an experiment on the International Space Station to look for antimatter, flying through space. Maybe it's out, maybe it went off to the left at the beginning of the universe, right? That's as good a theory as I've heard, okay? And maybe some of it comes flying around. They're looking for it. What I do is try to study the antihydrogen atom. The laws of physics, as we understand them, say that they should have the same color. In other words, they like to absorb and emit light. You know, like the street light looks yellow. That's a characteristic of a sodium atom. This laser pointer is green. It has a particular wavelength and frequency of light. CPT tells us that these two things must be identical. All right? So that's what we're trying to do. We have to make our antimatter and compare it to hydrogen, which we understand very, very well. Okay. How could you not work in Denmark and not want to know this? Because Niels Bohr is the national treasure. Just one quick word about precision. If I measure something at 1 meter with a tape measure with a millimeter precision, that's 1 part in 1,000, right? You got that little thing that slides at the end. You never know if it's where it's supposed to be. If I measure hydrogen color, the frequency of the light, we can measure that to 1 part in 1,000 trillion. It's like the 4th best number that we know, all right? My crew, the Alpha experiment at CERN, is all about doing that. There's the first ever Alpha machine, first ever to create and trap the atom of antihydrogen so we could shine some light on it to see if they're the same. That's the second one, second generation, just so you get an idea of what these things look like. And the third one is about gravity. What happens if I drop some antimatter? For matter, we know gravity is universally attractive. For antimatter, we just don't know. This has never been possible to do this. I now have the machine to do this. It's called Alpha G for gravity. And we're currently right in the middle of answering this question. So just some gears, so I'll show you some pictures of what this stuff looks like. The collaboration is about 60 people, right? This is what we do all day long. Okay, so we'll hear about the spaces in between. What's the space in between what we know and what we need to know? Well, we know now that antihydrogen is the same as hydrogen to about 1 part in 1 trillion. We need to do this about a factor of 500 better, 400, 500 better, to have the same knowledge they have in hydrogen. We want to know what happens to antimatter when you drop it. Okay, does it go down? Does it go up? Does it go down with the same rate? We need to get this published so I can tell you about it. Okay, 72 people in this corner of the universe know the answer to that. It would take longer than the age of the universe to make enough antimatter to blow up the Vatican. Okay? It would take more energy than we know about. It's a complete loser. A gram of antimatter could put a space shuttle in orbit or blow up the Vatican, but it would take longer than the age of the universe to make it. When this movie came around, the producers came and visited us, and I explained this to the guy from the Discovery Channel. And he nodded, and then he said, Jeffrey, does this mean that you would recommend nuking the Vatican? You got to be careful what you say to people.